Welcome to a lesson on the shell method for determining volume. This video will only show rotation about the x-axis. There are other videos that show rotation about other axes. To develop the idea of the shell method, let's go ahead and take a look at an animation. If we wanted to determine the volume of the solid generated by rotating this gray region about the x-axis, we could determine it by shells created by very thin rectangles bounded by these two functions rotated about the x-axis. If we rotated this very thin rectangle about the x-axis, it would produce a shell as we see here on the right. And the idea behind the shell method is, if we start to accumulate the volume of the shells as the number of shells increases, it will approach the volume of the solid, as we see here on the right. So as the number of shells approaches infinity, it will approach the volume of the actual solid. So to use the shell method to determine the volume, we really have to consider a single shell and think about how we would determine the volume of this shell. What we'd have to do is calculate the surface area and then multiply it by its thickness. So let's take this idea back to the presentation. If we were to consider the region bounded by this blue function and the x and y axis, and then rotate it about the x-axis, it would produce a solid that looks similar to this. Now, if we can understand how to determine the volume of a shell that will be generated by rotating a rectangle from the original region parallel to the axis of rotation, we'll have a much better understanding of how the shell method actually works. So if we were to cut this shell and unroll it, it would be a long rectangle where this distance here would come from the circumference of the circle, and that's equal to 2 pi r. And this distance here would come from the height of that rectangle. So to determine the volume of the shell, we'd have to take this surface area and then multiply it by the thickness of that shell. And with this orientation, the thickness of this rectangle would be delta y. So the volume for a single shell would be equal to 2 pi r times h times w for the width or thickness of that shell. And that's going to be equal to 2 pi times r of y for the radius function times h of y for the height function, and then times delta y. And so the actual volume will equal the sum of those shells as the number of shells approach infinity. So to formalize this, we have the volume is equal to 2 pi times a definite integral from c to d of r of y times h of y with respects to y, where r of y is the distance between the axis of revolution and the center of the rectangle, and h of y is the height of the rectangle. So the representative rectangle is really key to setting up and solving these volume problems. And for the shell method, the rectangle is going to be parallel to the axis of rotation. So if we're rotating about the x-axis, our rectangle must be parallel to the x-axis. So it might look something like this. And since the thickness of that rectangle is delta y, we'll be integrating with respects to y. So everything else must be in terms of y. R of y, the distance from the axis of rotation to the center of the rectangle, would be this distance here. And the height of the rectangle, would be this distance here. And this horizontal distance must be expressed in terms of y. Let's go and take a look at an example. We want to use the shell method to determine the volume formed by the bounded region rotated about the x-axis. So we have y equals x squared in blue, we have y equals 0, and x equals 2. So this would be our region rotated about the x-axis. So this is what the solid would look like rotated about the x-axis. And since we'll be using the shell method, the rectangle that would generate one shell would be parallel to the x-axis. So it might look something like this. And since the thickness of this rectangle would be delta y, that's telling us we integrate with respects to y as we see here. So let's go ahead and see if we can set this up. Our volume is going to be equal to 2 pi times the definite integral from c to d. Now the limits of integration must be in terms of y. So even though the x interval is from 0 to 2, we want the y interval, which will be from 0 to 4. Now we have to determine the radius, or the distance from the center of the rectangle to the axis of rotation. Well, that's going to be this distance here, which would be equal to y. We want to multiply this by the height of that rectangle. Now the height of the rectangle will be the distance from here to here, determined by the line x equals 2 and the blue function. It's going to take some thought to determine how to express this. It must be expressed in terms of y. So let's start by considering the distance from here to here. We know that's equal to 2. So if we take this total distance 2 and then subtract the distance from here, that will leave us with the height function. So the question becomes, how do we express this distance here? Well, this distance is x, determined by the function. However, remember this must be expressed in terms of y. So we have to take the function y equals x squared and solve it for x. We can do that by taking the square root of both sides. So we'll have the square root of y is equal to x. And since we're in the first quadrant, we'll only use the principal square root. So x is equal to the square root of y. So now if we take the value of 2 and subtract the square root of y, that will equal the height of that rectangle. So h of y is going to be equal to 2 minus the square root of y. And again, we're integrating with respect to y. So let's go ahead and simplify this. So we're going to have 2y minus y times, this would be y to the 1/2, that would be y to the 3/2. Now let's go ahead and find the antiderivative. So we'll have 2 times y squared over 2 minus, well, 3/2 plus 1, that'd be 5/2. So we'll have minus y to the 5/2 divided by 5/2, evaluated at 4 and 0. Let's simplify this one more time and then we'll perform the substitution. So we'll have y squared, and this would be minus, well, dividing by 5/2 is the same as multiplying by the reciprocal. So I'll have 2/5 y to the 5/2. So now we'll replace y with 4 and then y with 0. We'll take all of this and then subtract the value when y is 0. Well, when y is 0, both of these will be 0. And to save some time, I've already determined this value is 32 pi over 5, which again would be the volume of the solid generated by rotating this region about the x-axis using the shell method. Okay, I hope you found this helpful. There will be some additional examples in the next video.